Hello guys, this is Sina and tonight I'm gonna do this computer system architecture problem. Now I'm going to try my best to keep it short and straight to the point so you can learn it easily. Do you need to have any background to understand this? No, I didn't have any background and I hadn't really studied cache that much before this, but I could still understand it. So let's start. A byte addressable, and as you can see, the important part of the question are bold already, so you can see which things actually matter. A byte addressable computer has a small data cache capable of holding 8 32-bit words. Later I'm going to show you a table. I'm going to use this information, draw a table so you can visually feel it and you can see it. So each cache line consists of 2 32-bit words. So let's just draw this so far. We know what a byte is. 1 byte is 8 bits. And in 32 bits, there are 4 bytes, right? So 1 byte is 8 bits. How many bytes in 32 bits? 4. And each cache line consists of 2 32-bit words. So can you imagine it? Yep, easy. Here's how it's going to look like. We have 1, 2, 3, 4, 5, 6, 7, and 8 32-bit words. So each of these is 32 bits. And since we said there are 4 bytes in each 32-bit word, I just divided it into this shape. And the question says that each cache line or each cache block has 2 32-bit words. Now, what is a cache block and what is a cache line? They are exactly the same. Cache block is defined as the basic unit for cache storage. Cache line, same as cache block. Note that this is not the same thing as a row of a cache. So this row, when we talk about cache line, we don't mean one row. A cache line or a cache block depends on this computer. In this example, each cache line or each cache block is 2 32-bit words. So this is block 0 or cache line 0. This is line 1 or block 1, and these two are 2 and 3. Now, after this point, let's go read the rest of the question. So when a given program is executed, the processor reads data sequentially from the following hexadecimal addresses. What we know about hexadecimal is that each hexadecimal digit can be represented in 4 bits. Here's an example. 500 hexadecimal. If you want to write it to or convert it to binary, this is how it's going to look. 4, 4, 4. So in this example, because all of our addresses have 3 hexadecimal digits, when we convert them to binary, we're going to have overall 12 bits. So this is another important information that we need. And after this point, let's read the rest of the question and then move on to the solution. So this pattern is repeated 2 times. The cache is initially empty. Show the contents of blah 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 blah. If a direct mapping blah blah blah, hit rate. If you still don't know what the question wants from you, it doesn't matter. I had no idea either, but I keep proceeding to see what I can understand from it. So this question is not really meant to make sense because it's different. It's something you're experiencing for the first time probably. Anyway, so let's for the beginning start converting all of these hexadecimal addresses to binary. I've done it here and you can see all of these in binary. Now the next step and the next thing we want to do is to find out the value of tag, line, and word. Alright, I'm going to use a very simple and cool analogy here to teach you what we're actually looking for. So the next thing we need to do is to find out the values of tag, line, and word. Now, why do we need these things? How do we actually use them? You're going to see it very soon. Imagine, okay, we have 4 blocks. Imagine each of these bytes are one house. Our task right now is to find a number of bits to generate 8 unique addresses for each of these houses. So this is our question. How many bits do we need to generate 8 unique addresses? The answer is simple, 3. Why? Because 8 is 2 to the power of 3, so we need 3 bits to create or to generate 8 unique addresses. So this is one address, 2, 3, 4, 5, 6, 7, and 8. So let's say in each block we can say this is the 0th byte, this is the first byte, second, third, fourth, fifth, sixth, and seventh byte. And same for all other bytes. Now this is for bytes. So we can say the word is 3. How about lines? We have 4 cache lines or 4 cache blocks, since cache, line, and block are exactly the same. We have 4 blocks here. We need a number of bits to generate 4 unique addresses for each of these blocks. Easy, right? 2 to the power of 2 is 4, so we need 2 bits to do that. 1, 2, 3, and 4 unique addresses to, and you're gonna see we're gonna use these addresses later to locate data in these memories. Later, if you want to see if data is here, this is gonna be block 1, house number 012. So that's basically the idea, and I'm gonna show you later. So 3, 2, and since we said we have 12 bits overall, so tag is gonna be 7. 3 plus 2 is 5, minus 12, 7. Here's the binary equivalent of all of these hexadecimal addresses, and as you can see I've actually divided them into a line, word, and tag group. So since we have 3 words, you can see 3 bits here and line and tag as well. So how are we actually going to do this? What computer does here, and the question told us that the data cache is initially empty, so nothing is inside here. And this yellow doesn't actually mean anything, I just want to make it more visible for you. So let's become computer and see how it searches for data. So the computer wants to see if data, if there's data in this address. So 500 in binary is line 0, which is here, or this yellow part, and word 0. So this, we can assume this is 0, or you can say this is 0. It's just a logical presentation, so I don't think it really matters. So I'm going to say this is 0, this is 1, then 2, 3, 4, 5, 6, 7. So line 0, word 0, here. The data isn't there, so we're going to write it here. We go to the next one, 514. Line 2, word 4. Line 2, word 4. 0, 1, 2, 3, 4. Write it here. This was a miss, so is this. How do we define hit and miss? When computer looks for data in cache, if it can find it, it's a hit. If it can't find it, it's a miss. Right now we're searching, but there's nothing there, so it's a miss. So 3 to 8 goes to line 1, word 0. Line 1, word 0. 3 to 8. Miss. 3, 3C. Line 4, value 4. Sorry, line 3, word 4. So 3, 3C. This is the third line or third block, and this is the 4th byte in this block. 0, 1, 2, 3, 4, 5, 6, 7. And the next one is 444. 0, block number 0, and word 4. So it's going to sit here. It's in the yellow block. And one thing important we need to know is that every time we import, or every time the computer enters a new value, enters this block, it moves in and out as a block. Now this is a very confusing thing I'm saying. What I'm trying to say is that 444 moves in as a block and kicks the former block out. So it's not like we can have 1 byte and we keep the previous byte here. No, the whole blocks move in and the whole block will move out. So now we have 444 here, 500 is out. Does it mean this is a hit? No, that's a different definition, and we're gonna see it soon. This is another miss. 444. 2F0 is second line and 00. I'm gonna do this a bit faster because now I think you know it. This is gonna be 2F again, because it's in this block. The previous block will be swapped out. 200, 000 here. Again, this block will be out. 324, 004, 324. Block out, previous block out. 518. A third block 0 here. was it? 5, 1, 8. Again, new block in, old block out. 33C is here, this block, but this word, the fourth word. So this is 3, so I know that it's in block 3, and this is 4 in decimal, so I know it's here. And again, I kick this old previous block out. 4, 4, 4 again, we go up here. Now here, we have 3 to 4 at this position, and 4, 4, 4, let me highlight these. 3, 2, 4. You may think this is a hit, but no, it's not a hit. Even though 4, 4, 4 and 3, 2, 4 have the exact same word and line, and they actually seem to sit on the same place, this is not a hit, this is not a miss. Why? Because they have different tags, and that matters to us. A hit happens when two data have the exact same tag, line, and word. Here, if you look, they have this 3, 2, 4 and 4, 4, 4 have the same line and word, but obviously different tags. So we keep moving on. The last value is 4F4, which will sit in the second block because this is representation of 2 in decimal and fourth word of it. So 4F4 will be here, and this dude will be kicked out. So we did one round of searching for data. The question told us the cache was initially empty, so everything we did here was a miss. There was no hit. Now, as the question says, this process should be repeated twice. So we did it once, we need to do it one more time. We go back to the beginning and we repeat 0, 0, 0, 0. Where does it go? Here. Brother out, brother in. 5, 1, 4. Second line or second block here, block number 2, and fourth value. Again, it may seem like it's a hit, but it's not. Why? Because they have same line and word, but not the same tag. So 3, 2, 8. Block 1, value 0. Oh, this is a hit. This is a hit. Because 3, 2, 8 is already here, and again we're searching for it. Is it there? Yes, it is there. So this is a hit, and I'm going to show it with this X. So 3, 3C. Wow, it's again here. So this is another hit. 2 hits so far. 4, 4, 4, 0, 4. We go here. This goes out. Miss. 2F0. Block number 2, 0. 2FO. It's another miss. 200. It's 0, 0. Miss. 3, 2, 4. Here it's another miss. 5, 1, 8 is here and here. Miss. I'm gonna delete this, but we're gonna remember the fact that it was a hit. So 3, 3C, we write it here again. Another miss. 4, 4, 4 goes up here. Another miss. 4F4 comes, we're here. Block 2, value 4, 4F. Another miss. So we had 12 addresses, we repeated 2 times, so we had an overall of 12 times 2 equal to 24 attempts, out of which we had 2 hits, which means we have 2 out of 24 hit ratio. This is what we're looking for in this question. That's it, nothing else. I know at first it may seem really confusing and weird, and it may not make any sense, but it's not actually that hard. And yeah, if there's any question you can ask me, I'm gonna try to answer it. If I don't know, I'm gonna try to ask someone else. So yeah, thank you.